Hello, I'm Miss Manasir and this is the 6th video in my radioactivity series, and today we are focusing on fission and fusion, which is spec points 717 all the way through to 726. This is a topic that lots of people have asked me to do a video of. I'm going to try and explain it as clearly as I can so it's no longer something that you find confusing. So usually when I start off this topic I ask people to give me the link between all of these 4 pictures. You can have a little bit of a think, but essentially the answer is nuclear reactions. So that's what fission and fusion have got in common, is they're 2 different types of nuclear reaction. When we say nuclear reaction, what we mean is to do with the nucleus. So chemical reactions are all to do with the reactions of the electrons, but what we're talking about here is just reactions of the nucleus, so something different to what you'd have met before. Okay, so nuclear reactions as in only involving the nucleus. So this picture here that you'll recognise from that starter slide is Albert Einstein. I'm hoping that he's very familiar to face to many of you. He did lots of amazing science in his miracle year in 1905, and one of the things that he did was he published this equation, E equals mc squared. The letters in that equation stand for energy, mass and speed of light. So what he realised was, and we know that the speed of light is 3 times 10 to the 8, he realised that energy can be converted into mass, and mass can be converted into energy, which is now called mass-energy equivalence. If you think about the factor speed of light being in there, the speed of light is a very large number, but the speed of light squared is 9 times 10 to the 16. It's essentially an incredibly large number. So you don't need to know this equation, you don't need to know any of this history, but the takeaway from this equation is that energy can be converted into mass, and vice versa. But because of that conversion of the speed of light squared, this is the takeaway that fission and fusion are based on. If you destroy even a very, very tiny amount of mass, you can make an incredible amount of energy. And in both fission and fusion, both of these nuclear reactions, that's what we're doing. We just destroy the tiniest bit of mass, and the reason we would want to do that is to create energy, because energy can be used for many, many things. So I'm going to start with fission and then we're going to do fusion. Okay, so what's going on with fission? So with fission, you make fission happen by firing a nucleus at a large nucleus, sorry, firing a neutron, that's a neutron, I don't know if I said nucleus by accident, at a large unstable nucleus. There's a few different atoms that you can use, a few different elements rather, but the main one that we tend to use is uranium-235. Okay, that is it's already got a delicate balance of protons to neutrons, and actually uranium is the largest element you find naturally. If you fire that neutron in, what it basically does is it breaks apart the nucleus. So you need to know what you end up with. The nucleus in general breaks into kind of 2 quite big lumps, 2 quite big but smaller nuclei. They are called daughter nuclei. Sometimes the original one, using the same kind of terminology, is called a parent nucleus, which breaks into daughter nuclei. It also splits off and releases some neutrons that don't make up the daughter nuclei. So typically you give off 2 or 3 neutrons, and they're moving really, really quickly. Okay, what actually happens is if you look at the total mass of that neutron and add it up to the total mass of that large unstable nucleus, and then if you add up the total mass over here, what you find is there's some mass missing. So in this process of splitting up that large nucleus, some mass, I'm going to put disappears in inverted commas, disappears. Now where do we think that mass goes? well, it's from Einstein's equation, that mass is converted into energy. Okay, so that's the purpose. The whole reason we're doing this is we want the energy. So if you were asked to write a definition for fission, the definition is this. Fission is when a large unstable nucleus, such as uranium-235, splits due to collision with a neutron. The products, so the things you end up with, are the daughter nuclei and neutrons, and all of those have got a lot of energy. They're moving very quickly, so the type of energy they've got is kinetic energy. So that's the kind of definition for fission. So what we next are going to do is to look at when is fission useful. Okay, how can we use it usefully? So there are two main uses of fission. One is a use of controlled fission. One is a use of uncontrolled fission. So by controlled, we mean the amount of energy released stays roughly constant. By uncontrolled, we mean the amount of energy released rapidly increases over time. So what I'm going to do first is talk to you about uncontrolled fission, the second example here. So we've said that fission is caused by a neutron hitting a large nucleus such as uranium-235. One of the things that would produce is 3 more neutrons. So if each one of those neutrons can go on to hit another uranium-235, each neutron can cause another fission, and each of those in turn is going to produce 3 more neutrons, which in turn can produce another fission. Now each time that happens, there's going to be energy produced, energy produced, energy produced, energy produced. So when you've got this scenario, that is what we call uncontrolled fission, because we've gone from 1 to 3 to 9 neutrons very quickly, and that would continue to 2781. So this is uncontrolled fission, and that is what would happen in a nuclear bomb. Okay, so the use of uncontrolled fission is a nuclear bomb. Just to point out, the thing that is missing from that diagram is all the daughter nuclei. I haven't put them on because it just makes the diagram too confusing. So I've just drawn on the neutrons there and skipped the daughter nuclei. It is actually possible for fission to happen naturally, for a neutron to hit into a uranium-235. But what doesn't happen naturally is you don't get that much uranium-235 close together, so you never get a natural uncontrolled reaction because uranium-235 is too rare. So I'm just showing you this because it came up in an exam question a while ago, which was drawing your own diagram of fission. So from this start point, could you label the diagram and show what happens next? So you might want to pause the video now, and then in a minute restart it and I will show you. So I would label this neutron, label this uranium-235. First of all, I'm going to draw, coming off, the two big things, which are the daughter, missed out the T, nuclei, and I'm also going to draw the neutrons, and then I'm going to show at least one of those neutrons hitting into another uranium-235 to show that the process repeats. Okay, so I've got all the key labels there, and I'm also showing that this process can go on and on. Okay, so moving on then, we're going to now think about how do we go from this uncontrolled scenario, where you go from 1 to 3 to 9 neutrons and therefore fission events, to controlled fission. The way that we control fission is, if you want to have a controlled reaction with a constant supply of energy, what you need is a constant amount of neutrons. So if we start off with 1 neutron in this system, we need to only keep 1 neutron in the system at each time. So when these 3 neutrons here are released, we want to keep one of them and get rid of the other two. So if we get rid of those two, none of this and none of this is going to happen. Okay? For the next fission, we've got to do the same thing. We're going to keep this one neutron, but we're going to get rid of those two. Okay, so the reaction is controlled by absorbing unneeded neutrons. So, how do we do that? We use these things that are called control rods. So this is a different schematic of the same thing, just keeping one neutron in the system. So we're going to get rid of those neutrons, we've got to get rid of these neutrons, we've got to get rid of those neutrons. So what I've got down here is a schematic, a diagram of the nuclear reactor. So you can see I've got these kind of orangey coloured, what are called fuel rods. That's where the uranium-235 is put into the reactor. In between them you've got these green things here, which are called the control rods. So those control rods, we can think of them like sponges. They absorb neutrons and they can be lifted up and down to change the speed of the reaction in the nuclear reactor. So again, if you think about comparing it to a sponge, if you want a sponge to absorb a lot of water, it needs to have a lot of contact area. So on the left here, you can see that the control rods are all the way pushed into the reactor. So when they're pushed in, they've got a lot of contact area, so that will slow the reaction down because a lot of neutrons are absorbed. When we're pulling them out again, like we've got on the right, there's not much contact area, so not many neutrons get absorbed and the reaction can speed up again. Okay, so the reaction is controlled with control rods, and that allows us to carefully monitor the reaction speed. I'm going to talk you through another couple of features of a nuclear reactor that you need to be able to explain. The first one is the water. This diagram is not just coloured blue because of it looking nice. I mean, it's beautiful, isn't it? That is actually showing water. So that water, what it actually does is it slows down the neutrons. So interestingly, fission is more likely to happen from a slow moving neutron hitting the uranium-235 than a fast one. So the way that I think of this, it's a little bit like if you try and think about it, throwing a tennis ball and getting it to land exactly on a shelf. If you throw it too hard, it's just going to bounce straight off again. It's a little bit like that with neutrons causing fission. They actually are more successful if they collide slowly. So the water is what's called a moderator. That's an important key term you need to recognise. So what its job is to slow the neutrons down, and the reason it's needed is to increase the likelihood of fission. And what that effectively does is, and again this is a good phrase to use, it increases the efficiency of the nuclear reactor. So if you look back at your picture, I've explained what the fuel rods are, that's the uranium-235. I've explained the control rods, the green bits. I've also explained the blue bits, the moderator, the water. What I haven't the final thing I need to talk about is the grey around the edge. So what the grey is actually a layer of concrete. Okay, so that thick layer of concrete, which is usually at least a metre or if not a few metres thick, is called shielding. If you think about what a shield means, it's like a protective layer. The reason that that's important is because the daughter nuclei, the bits left behind after fission, are highly radioactive. So they're going to be giving out a lot of alpha, beta, gamma, all of which can be dangerous to humans as it can cause mutations of cells. So those used fuel rods we call spent fuel rods, they remain reactive after the fission for thousands of years. So getting rid of those spent fuel rods is incredibly difficult, and that's the main component of the radioactive waste from nuclear reactors. what do they look like, these really dangerous things? Nothing special. Okay, what they usually do is they get lined in concrete and lead boxes, and then stored underwater, and then move for a certain number of years, and then moved to store underground. But this is a really long-term problem. They last thousands of years, so much longer than any human lifetime, and we're running out of space. So if you want to do some extra reading about this, there's an interesting podcast by The Guardian called Toxic Legacy, which is talking about what we're going to do in England when our current storage solution fills up and we need to think of another thing to do. So that's everything you need really about nuclear fission. We're now going to go on to nuclear fusion. So fusion is similar but different. So fusion, if you think about the word fuse, means to bring together. So fusion is where you collide together small nuclei, such as hydrogen nuclei, and when they collide together, their combined mass is slightly smaller than their original mass. So again, some mass is, I'm going to put lost in inverted commas because it's not lost. What's actually happening? It's converted into energy. So you take two small nuclei and they are joined together to make a larger nucleus. So this is the word definition for fusion: the joining of two small nuclei such as hydrogen to make a larger nucleus such as helium, and as part of that process mass is converted into energy. Now the astute amongst you might notice that if you take a normal hydrogen 1 isotope and another hydrogen 1 isotope, that is not going to make helium because you don't have enough mass. So actually the complicated is quite a complicated process with lots of steps going through different isotopes of hydrogen and helium before you eventually get helium-4. But that's way beyond what you need, but I'm just mentioning it in case that was confusing anybody. So the next thing you do need to know about fusion after the definition is the conditions needed for fusion. So we've said that fusion is fusing together two small nuclei, but the problem is all nuclei are positively charged. So to try and hit together something that's positive and something else that's positive, what do we know? They are going to want to repel due to the electrostatic charges forces between them. So in order for them to actually collide into each other, they need to hit together very hard, so they need to have a very, very high speed, and they also need to be close together. So the conditions needed for fusion to overcome that electrostatic repulsion are high temperatures, very high temperatures, and very high pressures. So unlike fission, controlled fission and uncontrolled fission, this happens for a long time naturally inside stars. So all stars on the main sequence, including our sun, have got nuclear fusion going on inside. We've tried to make fusion happen naturally, and one of the devices we use, this is actually a picture of the inside. The purple gas, what that is a plasma. So you have to heat substances up that they're so hot that they become the next state of matter up from gas, that the electrons and the nuclei actually separate from each other and then fire them together. But what we're finding on Earth at the moment is it takes so much energy to create that plasma and to collide the nuclei that we're only just breaking even between the amount of energy we have to put in and the amount of energy we get out. So we're not able to use this at the moment for fusion power stations, but people are working on it, and if we do, it will be great because there's no nuclear waste here. So hydrogen is very plentiful, so there'd be a lot of advantages to getting fusion to work if we can do. So that is fission and fusion. We have talked about the fact that both fission and fusion are sources of energy. We've talked about the definition for fission. We have talked about the fact that the daughter nuclei are radioactive and we get a small number of nuclei. We've explained the chain reaction. we have explained the job of control rods, the moderator, the shielding, and we've talked about the definition of fusion, the fact that it happens in stars, and why it only happens at high temperatures and pressures. We haven't done really explicitly the similarities and differences between nuclear fission and nuclear fusion, but in brief, the main differences are, whereas nuclear fission is splitting a large nucleus, nuclear fusion is joining up small nuclei to create a larger one. The other big difference is that nuclear fission creates radioactive waste and has a very scarce quantity needed, which is uranium-235, whereas in fusion the hydrogen is very plentiful and there's no dangerous waste products. Okay, that is the end of my video on fission and fusion.